Hello, so welcome back where we are talking about the molecule urea and how we can use urea as the typical mineral fertilizer. And from the inorganic chemistry point of view, what we should know that whatever we are giving is your nitrogen, carbon, oxygen and hydrogen to the soil. So, the molecule urea, which is also historically very important, because it is the first molecule from a living organism, because urea, we know our body is also producing urea through the corresponding consumption of the protein molecule, decomposition of the protein molecule. As we all know, the protein is the big molecule out of the small building materials of amino acids. So, amino acids are nothing but NH2, CH2 is the smallest one, the glycine, NH2, CH2, COH. So, all these you have the nitrogen, hydrogen, carbon and oxygen. So, nitrogen, hydrogen, carbon, oxygen containing molecule we also produce. So, we also have the urea from our body. So, when people got it as the first molecule what we can have, whether we are able to synthesize in the laboratory. So, people were excited that time long back when it was first synthesized in the laboratory, which is in 1828. So, it is close to say basically 200 years. So, this 200 years of history is going to, because tell us that Friedrich Wöhler in Berlin in Germany, so he was trying to get it basically from a reaction of metathesis. The reaction he was being carried out is, one is your silver cyanate and another is your ammonium chloride. Why he was doing that particular reaction? Because his intention was very clear, that he knows, and the common knowledge or the prevailing knowledge at that time was that if you try to react silver ion Ag plus with Cl minus, we all know that from a saturated level, or because the silver chloride formed has a low solubility, because your Ksp value, the solubility product value is also very less. So, from silver cyanate will react with the chloride of ammonium chloride, giving you silver chloride precipitate, and what else? So, he was trying to make basically the synthesis of ammonium cyanate. Ammonium is the cationic part of ammonium chloride and cyanate is the anionic part of silver cyanate. So, he was basically trying to make ammonium cyanate. So, if he was able to make ammonium cyanate, but to his utter surprise, he found that is not a typical ammonium cyanate molecule, but it is something else that gave the birth of urea. So, some transformation will take place, and if that particular time the person or the laboratory available material or his perception basically tells that it is not a cyanate molecule, something or some rearrangement has occurred, and the character of that typical cyanate, because cyanate, the silver cyanate can be obtained from sodium cyanate is known, the character of this thing is known, and the character of the ammonium part of the ammonium chloride was also known that time. So, that particular compound what is obtained in their hand is not having ammonium part as well as cyanate part. So, it has lost its character in terms of its ammonium part or its cyanate part. So, it is something, the rearranged part what is obtained is nothing but your urea. So, that is the discovery of urea. So, urea plant basically nowadays large number of urea plants we have throughout all the different types of advanced countries, even in our country also. So, what we should have, because we now know that it is the corresponding ingredient is your ammonia. So, ammonia synthesis will be largely dependent on your urea plant. So, if the industry is interested to plant or industrially produce ammonia, they will have the urea also. So, side by side they can have two plants where ammonia is being produced and another part this ammonia is being consumed for urea production. So, what should be the first step following that Wöhler's technique or the Wöhler's reaction in test tube basically in laboratory? What he has done, if you go for a little bit of higher scale, we go beyond test tube to your round bottom flask of different size starting from 50 to 500 to 5 liters. So, the first step of that particular exploration is that ammonia and carbon dioxide is reacting. So, not that through that silver process. So, direct ammonia and carbon dioxide is reacting, giving you ammonium carbamate. So, it is basically simply the carbamate formation, the way we know that it can form the different types of carbamates of organic molecules also. So, CO2 as a gas, NH3 as a like an ammonia or liquid form, giving you NH2COO NH4. That means the ammonium salt of NH2CO, and the corresponding exothermicity of the reaction is known, the amount of heat liberated from that particular reaction is known. So, when we do this reaction, so how much we can convert from left to right, because all these reactions are reversible in nature. So, the reaction what we take it 70% of the carbon dioxide, because that is also a very useful technique where you can reduce the amount of carbon dioxide from the environment, because it is also a headache, is a greenhouse gas. Carbon dioxide is a greenhouse gas. So, it is required for our temperature rise of the globe, and also it is not helpful to increase the carbon dioxide in the atmosphere. So, if we are able to consume more and more of carbon dioxide, it will always be helpful for the environment. So, directly that CO2 will be converted to urea, and ammonia is only the starting material or the required material for its conversion. And this particular one, that the ratio of ammonia to carbon dioxide ratio, molar ratio is 4:1. So, more amount of ammonia will be required. So, you see that the reaction stoichiometry is 2:1, but we are adding a or going for a reaction which is 4:1. So, excess amount of ammonia should be there, and that excess amount of ammonia should be recycled. We should not lose that amount of NH3. So, the mass action basically will tell you that if we are able to increase the corresponding ammonia concentration or the pressure of the ammonia, because that is the only index of increasing the concentration of ammonia at a higher temperature of 200 degrees centigrade, and pressure is also higher, which is 250 bar. So, at high pressure and high temperature reaction, this reaction is forming, that we all know that how we make the ammonia through another very difficult process, which is the Haber process of ammonia synthesis from the elemental thing, that means the nitrogen or the hydrogen, that we have already seen earlier. So, this particular process we can have. So, this particular reaction basically that give you that corresponding decomposition, which is a reversible one. So, once you make this ammonium carbamate, so ammonium carbamate in the liquid form basically, so this is also a liquid urea in the liquid form, this is Q. So, this will be the liquid form, and water is also again in the liquid form, and this is a little bit of endothermic reaction of 15.5 kilojoule mole inverse. So, now this gives us the whole story, that how ammonium carbamate is reorganized or decomposition. So, basically we are following a decomposition reaction of ammonium carbamate with the liberation of water molecule. So, water you have to take out. So, one molecule of water, if you are able to take out from that particular inorganic salt, you are happy to get a compound which is your urea. And that urea basically, if I demand it, it should be an inorganic compound. It can be the origin from the living organisms, but it is basically an inorganic compound because it is produced from a particular inorganic salt, and its all other implications are similar to that of your ammonia or carbon dioxide. So, making this thing is also from the reaction mixture. So, the excess amount of ammonia, what is happening there? So, since the mole ratio is high, the molar ratio of 4:1 is giving you a reaction where you have extra ammonia there. So, the excess ammonia has to be removed from the reaction medium, and you can have a aqueous solution of urea, ammonium carbamate as well as ammonia. So, all these are there, and selectively you have to crystallize urea from that medium, and whatever ammonium carbamate is produced, which will undergo thermal decomposition. So, simply heating of the ammonium carbamate will give you urea. So, the heating process will also be responsible for your basically the thermogravimetric degradation product of urea, that because it is losing one of the water molecules. So, nowadays if a experiment is given to the students in the laboratory, that you go for a thermogravimetric estimation or gravimetric estimation of urea, what will you do? You will just simply go for its corresponding thermal degradation of ammonium carbamate. You will find a very distinct loss due to the removal of your water molecule at a particular temperature, where water is removed, which will be beyond 100 degrees centigrade. It is not that of your water of crystallization or the water tapped in the material. So, we can have huge amount of production or large scale production basically, because the most of the country are producing huge amount of urea, because urea has a huge demand in different industrial sectors. So, one of the particular process is the Boss-Meiser urea process. Boss is the name, will immediately tell you, it is from the German origin. So, the people, you see that it was first prepared in Berlin. Friedrich Wöhler did it in 1828, but you see it took around 92 years to produce industrially the large amount of urea by this particular process, and it was the major process basically since 1920s for urea production through this particular process. So, what we can have now, that if you go for a technique where you have the solution technique, so solution process, the reactors and everything is handling in solution, and the excess amount of one of the reactant is your NH3. NH3 is a gas. So, gas is coming out from the solution medium, and that we have to recycle. So, it should be known as the solution recycling process. The solution recycling process will now tell us how the corresponding excess amount of ammonia can be utilized. Since the reaction is a high temperature, high pressure reaction, so you have the pressure which we are applying on the solution, and the pressure applied to the solution leaving the reactor is reduced stepwise. So, you have the pressure inside the reactor, but when it is leaving the reactor you have less pressure, because it is released from that particular reactor. So, the carbon dioxide and ammonia released from that particular reactor, if some unreacted carbon dioxide basically and more amount of ammonia, because NH3 we are giving or you are using more. So, upon each pressure reduction step, so you have several pressure reduction step. If we are starting from say 100 bar or 50 bar of pressure, we just stepwise we are reducing one after another and return at their respective pressures to the absorber for absorption in water. So, ammonia can be absorbed in water, or CO2 can also be absorbed in water after you have reduced the pressure sufficiently. So, the flow chart or the diagram, what we can, this is basically a line diagram or line drawing, what you can consider, because you just have the orientations basically, because you must have a little bit of this thing in your mind, that where you can have, we are handling a little bit difficult thing, because industry people are mostly handling all three together, because they always expect also the solid product, but they are also handling the gas. They can have the industrial gas production also. We are having huge number of industrial sectors, the government sectors also, those who are handling gases, starting from your natural gases to any other specialty gases also. We have GAIL, we have Gas Authority of India Limited in our country. So, all these things, so what we can have, since ammonia and carbon dioxide now you can have, compared to our several previous techniques what we have seen, making of ammonium sulfate and all these things, that is this acid you are putting from the top and gas from the bottom, but here we are putting both NH3 and CO2 from the bottom of the reactor, because both of them are of gaseous origin. So, during the reaction, so this is basically the valve, you have the meter, the corresponding flow meter, and you know the internal pressure of the gas, because always we should monitor that particular chamber, the reaction chamber, the internal pressure, the pressure should not build up such that there can be explosion. So, that is you have, and then it is going from, so you can get it that one. So these two arrows basically, these two arrowheads basically pointing out that introduction of NH3 and CO2 to this particular reactor, and then it is going to the three other chambers of three different pressures. One is from 16 to 20 bar pressure within the chamber, another is 3 to 4 bar, and last is only 1 bar. So all these things are moving, and that movement basically going through this arrowhead, then this, then to this, then this, and then it goes basically, because all these three are basically the corresponding decomposer for the decomposition of your ammonium carbamate. So we are having now the corresponding urea solution. So this particular solution, when it is leaving this particular chamber, you have water externally, or you can put more mother liquor, and the ammonia as well as the carbon dioxide, which is then again condensed, because you release the pressure, there will be rarefaction, the dilute gases is there, so it will again be compressed. So as you are reducing the pressure in these three chambers, you can have also three different compressors. So condensers we call, so condensers. So this basically can give us directly from these particular heads, that means from the top, that means this will also release gas, this will also release gas, and this will also release the gas from the pressure release. So since we are reducing the pressure compared to the original chamber, so pressure release will take out that particular gas in this particular port, and this one, and so all three together can condense the gas molecules, and then again it can be inserted again to the reaction chamber. So that is the typical recycling process. So that's why the process is known as solution recycling process. So only thing that you should keep in your mind, that how the whole procedure is following and how that particular process is following for a recycling process. And if we can have a recycling process, we will be not losing any amount of those material, that material loss is minimized. So your production cost would be less, and so we can have huge profit out of this particular industrial procedure. So the chart or the diagram what is given is nothing but your flow sheet for a recycling process for urea manufacture. When we go for urea manufacturing, you should be able to identify the flow chart also. If the flow chart is only given to you, you should be able to identify it in terms of that, okay, it is the recycling process for urea manufacture. So if the diagram is given, you will be given 4 options for a multiple choice type of questions, what we can always consider, because otherwise we don't have any other options where you can draw it, we can write it, and you can level it all, this diagram, this flow chart. So remember that nicely in that way, that you should be able to identify or name the corresponding procedure for your urea manufacturing process. And everything what we are following, the entire course has been designed basically on this particular single book. So basically it is the Industrial Inorganic Chemistry, again from Wiley VCH and again from German origin, because that is the only country which is mostly important from the discovery to the industrial production of the chemicals, particularly the inorganic chemicals. So that is the country. So most of the time we have simply follow this particular book. We are indebted to that particular book also, because all these diagrams are also taken from that particular book. So if we have this particular book also, you can also follow nicely the thing what I am being taught here for in a stepwise manner. So urea now will just go from natural gas sources. So the natural gases which we all know, that is basically the methane. And the liquefied natural gases are we have, which is known as LNG, not LPG, it is LNG. Because this part of the country, the eastern part of the country, don't have that much source of natural gases compared to the western part of our country, where you have the Bombay High, the Bombay offshore. They are producing huge amount of natural gases, but they are now processing and all these things. Now they are bringing all these natural gases in the port of this eastern side by different companies. They are also bringing for our domestic use, for automobile use, and lastly for the manufacture of these important compound like the fertilizer, like urea. Because this natural gas or the methane can also be a source from the shale gas. So shale gas, if the shale gas activity by the geologists are increasing, So shale gas production is also increasing because small companies from western part is coming to this eastern part of our country, is also devoted to that particular shale gas for the manufacture of urea or any other nitrogen based fertilizer. So what basically we can have, because the challenge you should think of from academic point of view, because basically first you consider from this academic point of view the feasibility of the reaction, then the process development, the industrial challenges, and all these things will come afterwards. So the first thing what we can do is that you have the natural gas. So natural gas is mostly the hydrocarbon based on methane. So we go for partial oxidation. So if you have a hydrocarbon containing carbon and hydrogen and you try to oxidize it, what can happen? So originally you can have methane, so CH4 will be there. So we get basically raw, is not a very pure form. So is a raw synthesis gas will obtain through that particular partial oxidation, and is mixture of the original compound of this gas, that means the methane, along with carbon monoxide and carbon dioxide and some amount of hydrogen also. Some amount of hydrogen will also be there, because we all know that the oxidation of water as the another source of getting this synthesis gas will also give you a mixture of this hydrogen and oxygen and all other things like that. Carbon, when it is dropping on the coke, that will giving you carbon dioxide and carbon monoxide. But what we can do, that synthesis gas will be treated catalytically now, and we try to get the conversion of the whole thing. That means what we don't want, that means the water. As I told you that the reduction of water or the breaking down of water on the heated coke giving you hydrogen and oxygen, and that oxygen can be consumed for giving you carbon monoxide and carbon dioxide if the carbon is available in the form of red heat coke. But in this particular case, your carbon is available in the form of two oxides, that means carbon monoxides and carbon dioxide. So that carbon monoxide and carbon dioxide, whatever available, still there, but we go for the oxidation of carbon monoxide to carbon dioxide, and at the same time H2O will be converted to H2. So that is the most important part of all these reactions, that you have to have methane, then CO2 and H2O in that particular thing. So like a block diagram, block flow chart, you have two boxes only instead of drawing in a full form of reactors. So we will feed this particular chamber with natural gas along with water, because this air, because this air, why we are feeding air over there, because the air will be given for your oxidation, because here we are using this particular one for oxidation. So the step one is nothing but is autothermal reforming or partial oxidation. We call it as a partial oxidation. You see here we are written as partial oxidation, because we are not going for exhaustive oxidation, which is also known as autothermal reforming of the gases. You have the air. So we get CO2 as well as ammonia, because ammonia will be feeding over there. So ammonia we have to bring from somewhere else. So this chamber will only give us carbon dioxide and hydrogen if it is available, because this hydrogen will be the most useful one if we are able to get it from natural gas source, the shale gas source, or any other source of it, because that hydrogen will be combined with the nitrogen of the atmosphere. So atmospheric nitrogen will now react, because these are the raw material for the production of NH3 through Haber process. Two gases, nitrogen and hydrogen, will combine to give you the ammonia. So the excess amount of ammonia which is being introduced over here, so these two, again we have two gaseous thing, that means the way we get ammonia from the combination of nitrogen and hydrogen, one is very cheaply available from atmosphere and another only you have to bring hydrogen, is giving you the corresponding ammonia production, and that ammonia production again through the use of carbon dioxide, which is again the source of atmosphere. So atmosphere can give us carbon dioxide, but that carbon dioxide is not highly concentrated, so that's why you have to rely on synthesis gas. These two will give you for your step 2, that means step 2 already we have seen the reactor thing and all these things. So we'll couple this for the step 2 part. So the previous flow chart for the diagram, the flow sheet will be attached over here to make you more and more amount of urea. Thing is that your starting material or the starting thing is your natural gas. So, the feed basically in this particular point, the CO and CH4 which are there. So, already you have CO and CH4, so can be removed because we do not need these two for your urea production. So, we have a step what is known now as the gas cleaning process or gas cleaning step. We are cleaning some part of the gas. So, those gases, the carbon monoxide and methane are driven away, only hydrogen is taken care of. So, hydrogen is now converted to ammonia upon addition of dinitrogen. So, N2 will be used for your useful production of NH3. So, that useful production of NH3 will now take you to that step 2, which is your step number 2, which is B step. So, B step will then you have very simple one, we combine with previously separated CO2 because CO2 was separated earlier. So, there is no need to bring CO2 because CO2 was already there in your natural gas, in your synthesis gas. So, only thing that your separation of CO2 earlier such that this CO2 should not go out along with your carbon monoxide, it should be preserved or it should be kept for only reaction with NH3. So, that only reaction with NH3 will tell us that the use of that particular CO2 what was originally available should be consumed for your urea production. Then we will just quickly see how these are very important areas of application of urea. So, raw material, it is basically a raw material for the production and manufacture of two main classes of material. One is nothing but is a very simple compound which we call as the urea nitrate. So, urea we have free NH2 end like your ammonia. Ammonia is giving you the ammonium type of thing, addition of one more proton on the nitrogen. Similarly, urea can take up extra hydrogen to make it urea cation. So, dicationic form. So, which can take up the nitrate as your corresponding explosive like your ammonium nitrate. So, this can also be utilized for some improvised explosive devices for blast making some expedition, geological expedition and all these things. So, we require always research and development quality explosives, the RDXs we all know. So, regular improvement of all these RDXs are there. So, urea can one of the component in terms of your urea nitrate. Then the urea formaldehyde resin and the urea melamine formaldehyde resins are also there for the production of plywood which is used for the marine water or the sea water. So, it is a marine type of plywood. So, which will also resistant to the material what is present in your sea water, which is much more corrosive than that of your pure water system. So, urea is taken up with formaldehyde for a polymerization. So, resin making urea is one of the component. Then you can have along with your melamine. Melamine is again a nitrogen based cyclic molecule. So, melamine along with formaldehyde. So, it is a 3 component resin have some improved quality. So, that improved quality of that urea melamine formaldehyde is utilized for making these. So, how this particular one is reacting. So, the urea formaldehyde structure you should know a little bit of this particular structure. So, again in the next class we will start from here basically. So, we will not follow the other part. So, the other part will follow will complete over here this particular thing. So, the formation of this urea and with that of your formaldehyde giving you the corresponding one, this NH2 will be converted to NHCH2O. So, that is the most useful reaction of any nitrogen based compound, any phenol based compound with that of your formaldehyde. So, once you get this particular introduction of your alcohol part along with your NH part, so it will be a very highly reactive part. So, there is a this amine alcohol. So, the amine alcohol part starting from this is very reactive one. So, n number of such amine alcohol part will be then polymerized to give you the corresponding resin part, which is after curing give you a very solid product, and that solid product is also chemically resistant. And there are lots of applications because the resin application will follow afterwards and we will just categorize this in terms of the resin use and resin making of all these things, and that is concentrated on resin making only. But here we are talking in terms of only the use of urea. So, next day we will complete the urea use other part and we will follow that one. Okay. So, thank you very much.